Hi, my name is Shalia Lopez, and this is my Lab 3 of a Black Hole for Physics 2211 with Dr. Yonker. So our purpose in this lab, first of all, it was computational, unlike the other two, and it was divided into two parts. So for the first part, our purpose was to calculate the mass of a black hole by the universal gravitational force between a star of known mass and the black hole, and we did this through the use of glow script. And the second part, it was to determine the initial velocity needed to launch a spaceship to get it close enough to the black hole without crashing and still be able to leave the system. The fundamental principles that we needed to know for this lab were Newton's second law, where F net is equal mass times acceleration, and it also had derivatives in multiple ways of expressing it, as well as the law of gravitation and the position update formula, as well as the velocity update formula. Fundamentals that we need to know are the parallel and perpendicular components of the net force, which in this case is the gravitational force. So the parallel component is also known as p hat. It's the one that's parallel to the direction of motion. The positive p hat is pointed in the direction of motion, and it tells us if the object is speeding up or slowing down, and it is related with the change in speed of an object. Perpendicular component, it is known as n hat, and the positive n hat direction is directed towards the center of the orbit, and it has to do with the change of direction of an object. So for the first part of the experiment, this is the code that we have. So first here we have the initial conditions, we have the mass of the start, the change in time and the initial time, and here we have a massive code where we found the initial and final momentum vectors. We calculated the star's change in velocity and change in momentum. We calculated the dp over dt, and we used Newton's second law to calculate the net force. Then we also calculated the parallel and perpendicular forces, as well as the net force for both of these, in order to calculate the mass of the black hole at the end, which is this last code that we see here. After doing this, in which we had that the system was the planet and the surroundings, everything else, especially the black hole, we have that the mass of the black hole is 9.58 times 10 to the 23 kilograms. We were given multiple masses during each iteration model. So because of this, our possible source of error could be the rounding volumes during each of this step. We have our magnitude of the net force and the magnitude of the parallel, as well as the perpendicular net force. Now moving on, we have our second code, which we also have the initial conditions. We have the mass of BH, as well as the gravity, the mass of the planet, mass of the ship, and the change in time. And here we found the force of gravity on the planet by the black hole, the force of gravity on the planet by the spaceship, the net force on the planet, and then we did pretty much this entire same process to find the force of gravity on the spaceship by the black hole, also the force of gravity on the spaceship by the planet, and then the net force on the spaceship. For this case, our system was the spaceship and the surroundings were the planet and the black hole. We have our initial velocity of the spaceship, which is negative 4.58 times 10 to the 7, 2.5 times 10 to the 6, 6 meters per second. So we know that velocity when leaving the planet, and though it comes close to the black hole, it is able to leave the orbit and not crash with the black hole or the planet. And we have that the x direction is in the negative direction, because as we can see in the initial velocity, the x component is negative. Possible errors that we could have in this process were the approximation, since this is a simulation, so it would not always represent reality, as well as accuracy, because we use trial and error to find velocity. So there could be more precise velocities that get to the spaceship closer to the black hole. So what does this mean? And how is the net force and its parallel and perpendicular components different from the rate of momentum and its parallel and perpendicular components? Well, mathematically they're the same, but one is easier to measure than the other. So for the net force, we must know each individual outside factor exerting a force on the system. And for the rate of change, we just need to know the system change in velocity and motion. But what if and what initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? Well, the initial velocity would be negative 5.06 times 10 to the 6. comma 2.5 times 10 to the 6, which is pretty much double the y component, but in the x direction.